Now we want to introduce the idea of torque. And this is another word that kind of like work, it's used in everyday terminology, and not all the time is it used in the purely scientific sense. So we're going to define torque as force times lever arm. Okay, so what this means is that if I apply a force in a rotational sense, then the overall we don't want to use the word force again, but the overall effect that the object feels, if you apply a rotational force to something, the overall effect that it feels is going to be determined by both the force and the length of your lever arm. So where do we see examples of torque? Well, the most common example of torque is using a wrench. So if we have a stubborn hex nut here, and we're trying to turn it with a wrench here, so here's our wrench, and we're trying to turn this stubborn bolt. Okay, so the center of the bolt is right here, and we're typically, if we're going to loosen it, right, we're going to turn it this way. So the whole idea is that you apply a force on the wrench by trying to push it up this way, and our arrows are getting a little mixed up here. So the rotation is going to be this way, and the force that you apply is going to be more or less straight up, and the lever arm is the distance from where you apply the force to the center of rotation. So the bolt is going to rotate around its own axis, and so we denote this length here to be the lever arm L. And as the popular saying goes, if at first you don't succeed, get a bigger wrench or get a bigger hammer. The whole idea is that if you get a larger wrench and you're able to increase your lever arm, then you're able to increase the torque, you're able to increase the effect. And so if we get a larger wrench, if we can't turn this stubborn bolt, and we get a larger wrench, and we increase our lever arm, then we can still push upward with the same force that we were before, but the overall effect that we're going to put on the bolt is going to be greater. Okay, so that's how torque works. Now there's lots of places that torque comes up, but your book gives a couple of specific examples, and that's what we want to look at. So now what we want to look at is the teeter-totter, or the balancing act. So let's say that I have a balance beam, and it's sitting on a balance, and I put an object some distance x0 away from the pivot point. And by the way, the pivot point has a special name. We call that the fulcrum. And if I wanted to put an identical mass, on the other side so that it would balance, well, first of all, we know that under this condition, if this is a fair balance and the plank itself does not have more weight on one side than the other, then without the mass here, it's going to balance, and then as soon as I put the mass on, it's going to tip up on this side and it's going to go down on that side, right? So it won't balance. So if I want the beam to balance, I have to put something on this side, and if I want the object to be the exact same mass, then I'm going to put it the exact same distance away from the fulcrum so that these two distances are equal. Now, why do I want to do that? because for balances or teeter-totters to balance, okay, for, we'll call it TT for teeter-totter, for teeter-totters to balance, the torques must be equal on each side. Okay, so for the teeter-totter balance, the torques must be equal. So, if I have a balance, and I have a weight here, and I have a weight here, what are the torques? So let's let this be mass 1, and we'll let this be mass 2, and what are the torques? Well, mass 1 is going to put a force equal to its weight downward that causes a rotation of the plank, and that weight will be weight 1, which is just m1 times g. And the second mass, so weight 1 is going to cause the beam to rotate that way. And if we ignore weight 1 and just look at weight 2 is going to cause the beam to rotate this way. And it's going to push down on the beam with a weight W2, which is equal to M2G. So these are the forces that they put on, and then the distances away from the lever arm, we'll call this D1, and we'll call this D2. The torques, and we denote torque by the Greek letter tau. Okay, so the torque from the first mass is going to be its force times lever arm, which is just going to be its weight times its distance, d1, and torque 2, the torque by the second mass is just going to be equal to its weight times its distance. And so they balance when these two expressions are equal. Okay, so they're going to balance when these two expressions are equal. So if M1 and M2 are equal, then D1 and D2 must be equal. But let's look at a situation where that's not necessarily the case. So let's look at a teeter-totter on a playground where a parent is playing with their child. So over here we'll have a small person, and they're going to be on this end of the teeter-totter, and on this end we're going to have a parent, say a dad, who's much larger, and they initially arrange themselves so that they're both sitting on the seats that are on each end. And we'll say that the seats are each 2 meters from the fulcrum. Okay? So each lever arm is going to be 2 meters from the fulcrum. Now let's let the child have a mass of 20 kilograms. We'll put MC for the mass of the child. We'll let him be 20 kilograms. And the mass of the parent, we'll let them be 65 kilograms. So if they both sit on the teeter-totter in this arrangement, what is the overall torque, or what is the total torque that the teeter-totter feels? Well, we all know from experience that the heavier parent is going to rotate down and just sit there unless they push up with their legs, and the helpless child will be thrust up into the air like this. But the overall torque is just actually going to be the sum of the torques, and so the parent's torque is going to be the weight of the parent times the distance. Now, here's the thing about torques. if we go back to this slide, M1 causes a downward rotation like this, whereas M2 causes a downward rotation like this. Okay? And we define counterclockwise to be positive. So if the mass 1 causes a rotation counterclockwise, it'll be positive, and torque 2 will be negative. So in this case, the parent will cause a counterclockwise rotation, and the child would cause a clockwise rotation, so the child will have a negative torque. So he's going to have a minus sign in front of him. And again, this is just going to be the mass of the parent times the distance times gravity. mgd minus mcgd. Okay? So this is the total torque. And if we calculate this out, parent's mass was 65 kilograms times 10 meters per second squared for gravity times 2.0 meters minus 20 kilograms times 10 meters per second squared times 2.0 meters. And this comes out to, well, 65 times 10 is 650. 650 times 2 is 1300. And we're going to get, note, kilograms times meters per second will give us newtons. We have another meters, so this looks an awful lot like joules, newtons times meters, but we don't call it joules. We just leave it in the term Newton meter, and that allows us to differentiate between talking about energy and talking about rotational motion, okay? Talking about the units of torque. So this is going to be 1300 minus, well, 220 times 10 is 200, times 2 is 400, so minus 400 newtons times meters. So this has given us an overall torque of 900 newton meters. And because it's positive, that means the counterclockwise rotation wins, which means that the parent wins, and the teeter-totter would behave just as expected. It would go down, and the parent would sit there on the ground. So now the question is, where should the parent sit for the teeter-totter to balance? And the issue is, when the teeter-totter is balanced, if we go back a few slides, for the teeter-totter to balance, the torques must be 0. Okay? So the sum of your torques must add up to be 0. And so, what we can say is that torque total, which is equal to the torque of the parent minus the torque of the child, must be equal to 0. And that means that the torque of the parent must equal the magnitude of the torque of the child. And so now we can calculate this out. So now we're no longer holding the parent to sit at this 2 meter distance. He can scoot up. Okay? Well, he obviously can't scoot back, but the question is, at what distance d must he scoot up if he is to balance out with the child? And they'll be able to actually play on the teeter-totter at that point. And so, the torque of the parent, if he moves up, is now going to be m1gd, whereas the torque of the child is going to be m2g times the 2 meters. And notice we have g on both sides, so those can actually cancel out. And so the distance is actually going to be the ratio of the masses, m2 over m1, m2 over m1 times this 2.0 meters. And so, if we do this, m2, remember, was 20 kilograms. The parent was 65. And we multiply this, we multiply this by 2. Meters. So our final units are going to be meters because our kilograms are going to cancel out. We're going to be left with meters. And if we take 20 and divide it by 65 and then multiply it by 2, we get 0.615 or approximately 0.62 meters. So the parent needs to scoot up to a distance of 0.62 meters away from the fulcrum for this to balance. And at that point, they'll both be able to do the teeter-totter. So that is a short introduction to torques, and in the next video we will talk about angular momentum. We'll see you then.